Today, we're going to talk about absolute convergence. This is not a way to test whether a series is convergent or divergent. It's not another type of test. It's just a type of convergence. So if we look at a convergent series, there's something that's even stronger than being convergent, and that's being absolutely convergent. To be absolutely convergent means that the series and its absolute value both converge. But let's look at an example here. So if I look at this example here, this is our alternating harmonic series. We saw that by the alternating series test, which I won't write out all the details here, but by the alternating series test, this guy converges. So that's great. Fine and dandy. But now for absolute convergence, what we're going to ask is, if I take the individual terms and I take their absolute values, does that thing converge as well? So if I take the absolute value of those terms, the -1 goes away, so I just get 1 over n. That's the harmonic series, or a p series with p equals to 1, so this is divergent. So the series itself converges, but its absolute value does not. So in this case, what we're going to say is that our original series is conditionally convergent. If both of these were convergent, then it would be considered absolute, or it would be called absolutely convergent. So what we're going to learn is that we're going to learn to test the root and the ratio test eventually. The root and the ratio test are going to tell us whether things are absolutely convergent or divergent. It turns out that if the absolute values converge, if the absolute value of the terms converge, then the original series converges as well. So if we look at the absolute values and we get something that's absolutely convergent, then we don't have to do more work. Our original series is also convergent. So things being absolutely convergent, just a little bit stronger than conditionally convergent. Let's look at this one here. So we could start by looking at the absolute values and just see what happens, because if the absolute value converges, then the original series will be absolutely convergent and hence convergent. So let's do that. If the absolute values do not converge like they did in the last case, then we'll have to go back and look at the original series. So let's look at the absolute value. So if I take the absolute value, the -1 piece will just become 1, so we get 1 over n squared. This is a p series with p equals to 2, which is bigger than 1. So this is convergent. So the absolute value of our original series converges, which means that our series is absolutely convergent and hence convergent itself. So it is absolutely convergent. Yay. Okay, so let's see if we do the same thing in this next one here. If we look at the absolute value of the terms, once again, the -1 will become a +1. This is a p series again with p equal to 1/2, but that's less than 1. So the absolute values diverge, which means that there's 2 options for our original series. Our original series cannot be absolutely convergent because the absolute values of the terms don't converge. It could be divergent or it could be conditionally convergent. So let's see what happens here. So let's try an alternating series test on this. So certainly it is alternating. If we look at the limit of the absolute value of the terms, that is equal to 0, which is good. And the sequence 1 over root n is definitely decreasing. So we've met the 3 conditions for the alternating series test. So it converges by the alternating series test. And since our original series converges, that's not how you spell converges, but the absolute value does not, then we say that our series is conditionally convergent. So we'll do some more examples like this in class. And then, like I said, we will learn to test, which will just tell us whether things are absolutely convergent or divergent.